Today, I'm really excited to have Zoltan Varga here from the Wigner Research Centre for Physics in Hungary. And most of you all met Zoltan over the past 2 summers. He was a visitor here in our group last summer and the summer before, so it's great to have him back virtually. Zoltan completed his bachelor's degree at Eötvös-Loránd University and his master's degree at Budapest University in Hungary, where he was actually in the lattice theory group. Currently, he is in the final stages of his PhD at Budapest University, and he's a junior research fellow at Wigner. Zoltan research focuses on investigating KNO scaling, both from a phenomenological perspective and also doing data analysis through the ALICE collaboration. Yeah, so today Zoltan will tell us about studying multiplicity dependence of jet properties and the role of the underlying event and NPA collisions. Yeah, so Zoltan, whenever you are ready, please go ahead and start.
Thank you very much, Laura, and it's good to see everyone again. And please stop me anytime if you can't hear me properly or you have any questions. I'm going to give you an overview of the research I have done throughout my PhD, and it will consist of separate topics, including data analysis and some phenomenological studies, but hopefully I will be able to make a connection between them. And the overall message will be to propose new measurements, which would be very important to do, in my opinion, in the upcoming era of ALICE. So here is just a short outline. After a brief motivation, I'm going to jump into the jet measurements, where I was focusing on specifically multiplicity measurements and the study of jet scaling effects. And then I'm going to discuss heavy flavor measurements and try to propose new studies, which is essential, in my opinion, to progress in the field, as you will see. So first of all, what is our goal? We want to understand and uncover the basic building blocks of our universe. And thankfully, we can actually create a so-called little bang in the laboratory by colliding heavy ions together and create this so-called quark-gluon plasma and then study its properties. However, small systems are still very interesting when we only collide proton-protons together. And in this talk, I'm going to focus on these small systems and try to show you that they can still be very interesting, not only the heavy ion collisions. And of course, I'm going to connect my studies to future heavy ion studies, because these measurements can be and should be extended to heavy ion. So some interesting results, for example, the collectivity in small systems, if we consider high multiplicity events at LHC energies, this is the so-called flow. Our current understanding is that quark-gluon plasma formation is not necessary to explain these collective effects. It can be done so with utilizing vacuum QCD effects, which affect these soft-hard boundaries. And here comes the multiple proton interactions, which again can be used together with caloric connection effects to explain these results. So here already you can see that multiplicity is a very interesting area to study. And jets are very useful, not only in heavy ion collisions, but also in proton-proton collisions. Even though jet suppression is not expected, they can still be used to study this boundary between the soft and hard processes, which are related by the MPI, or multiple proton interactions. So first of all, I will try to build up the motivation toward the data analysis that I am doing with Laura and Robert at the moment. And just try to move this cursor. So we can measure the jet profiles One of them is the so-called differential jet shape. I haven't included a figure, unfortunately, but it just provides information about the radial distribution of the jet PT inside the jets. So we just divide the jet cone into these annuli and count the jet PTs and see how they are distributed, and we get a nice function. And we can do this as a multiplicity study if we create different multiplicity classes. Here in the figure you can see many different multiplicity classes shown by the different colored curves. And again, these curves give you the multiplicity distributions inside the jets. Here we considered 0.7 jet resolution parameter. You can see that as you go to the far outer region of the jets, you have a smaller momenta fraction. And what's interesting here is that these different curves all intersect each other in the same point, at least approximately. And what we have done was to consider different generators. One of them was, of course, the well-known Pythia Monte Carlo generator. The other one was a new generator still under development, which is the Hygiene++. This is capable of simulating heavy ion collisions as well. We also consider different so-called tunes. So these event generators are tuned to different collision events, and then we can use these different physics, so to speak. We consider different parton density functions. We considered color connection schemes and different multiple parton interaction settings, and of course, different jet algorithms, including the well-known NTKT, the Cambridge-Aachen, and the KT algorithms. And what's fascinating in this behavior is that all of these curves intersect each other at the same point. And they are totally independent of these different settings that I have listed here. And there is still no explanation for this behavior. We suspect that it might be a sort of scaling behavior. And it can also be a sort of artifact coming from the Monte Carlo generator itself. However, since we use different Monte Carlo generators, this sort of rules it out. And in any case, this was my first jet structure measurement, and it would be really essential to do this measurement in Alice data to see what we find and if there is indeed this scaling present. However, yes? Sorry, I thought there was a comment. So we can actually investigate a different kind of scaling as well. And this has been done recently in 2021, where these jet profiles that I showed you were parameterized with a gamma distribution. And it was shown that it scales with the event multiplicity. So this is a sort of scaling that was shown to be present. And then the question arose whether these multiplicities are scaled with the jet momentum. And if this is true, then this would be something similar to the so-called KNO scaling. I will go into details later. But the point here is that it was shown that these jet-shaped curves indeed scale with the multiplicities. And then the question is whether a KNO-like scaling is present or not, because that will be very interesting as well for many model developments. And it was also asked whether the scaling are modified with considering heavy flavored jets. And this is another study that was done by me, where I showed that the scaling is still present, this KNO-like scaling, if we consider differently heavy flavored jets. And going back to this R-fix phenomenon, this that I showed you, that all these multiplicity jet-shaped curves intersect each other at the same point. Here I plotted this R-fix in terms of the jet PT windows, and you can see that it is shifted as we go to higher and higher energy jets. So in a sense, it behaves as if it was some kind of correct characteristic jet size, which would be very interesting to attach some kind of size to these jets, because as you know, it's just very vague how we define them. And it is indeed modified by considering differently tagged jets. So this is the motivation. There are many phenomenological studies, different kinds of scalings has been uncovered. The question is what we see in the data. So first of all, let me go into more detail regarding this KNO-like scaling, and then I will go on to the measurement itself. So the KNO-like scaling has been proposed by Koba-Nielsen-Olesen in 1972, in which the event multiplicity distributions are scaled with the center of mass energy. However, the scaling is violated at high enough energies, and the reason behind this is still not fully understood. However, recent studies suggest that it might be because of the presence of multiple parton interactions or overlapping color strings. And the question is, again, what happens within single jets in data? And can we quantify the presence of the scaling or not? And what we set out to do is to measure the scaling in Alice data. And I want to mention already here some interesting questions, like what is the origin of the scaling? Does it have any jet size dependence? Is it violated in larger systems or not? So this connects it to the heavy ion collisions. Is there any flavor dependence? In simulations, there is flavor dependence, but it's a question whether it is in data or not. And so on. There are many interesting questions that can be investigated. Here on the left-hand side, I just included two figures. Here on the horizontal axis, you can see the scaled multiplicity. This is the event multiplicity scaled with the average multiplicity. And on the vertical axis, you can see the average multiplicity, the event multiplicity again scaled with the average. You can see that all these curves can be collapsed onto a universal curve. This is what the scaling is basically. And it was shown to be present in both electron-positron collisions and proton-proton collisions before. But again, if you go for high enough energies, then it is violated. The difference in our case is that we want to consider jet multiplicities, not event multiplicities. And instead of collision energies, we want to consider jet PTs. So this is why we call it KNO-like scaling. So this is not the KNO scaling itself. So what is our observable? First of all, we can do this same multiplicity scaling and try to collapse all these different multiplicity curves onto each other. This is what you see on the left picture. The different symbols represent different jet PT windows. You can see that there are quite many, from 15 GeV over C up until 4000. And all these can be fit onto each other. So this is just an example of what we see in simulations and what we expect to measure in the data. And another way to quantify this scaling is to calculate the statistical moments. We did this up to the ninth statistical moment. And it's basically, we plot the nth moment of the the expectation value of the nth moment of the multiplicity, taking the logarithm and dividing by the moment. And we plot this in function of the average multiplicity. And it can be shown mathematically that if the scaling is present, then we expect curves with a unit gradient for all these different moments. And if you go for higher moments and these start to differ from a unit gradient, then you have a violation in this scaling. Of course, we don't really expect a perfect scaling, but this will quantify how much it is fulfilled. And for this, again, we need to extract the multiplicity distributions and plot them as a function of the jet momentum. And we parameterize these with negative binomial distributions. Again, what you see on the left picture. And if they all can be collapsed onto a single MBD curve, then we have this scaling. For the Alice data, we need to correct for the detector effects for which we have used two-dimensional unfolding. So we measure the jet PT and jet multiplicities both on the reconstruction level and the true level. And here I listed the bin selection. This can be modified to make it more finer, but since the multiplicity distributions are shifted with the jet PT, it's quite challenging to find a proper bin selection, which still behaves properly. Let me list quickly the systematic uncertainties which come into play in our case. Of course, the most significant contribution will be the tracking efficiency as expected. We also took into consideration the choice of the regularization parameter, the different prior distribution, and also did a change in the reconstruction level jet PT binning. And these four will be our sources of systematic uncertainties. This is a quite well-known sources, so nothing extraordinary in this regard. And here, let me plot on the left-hand side these different moments, again up to 9. And you can see that there is some difference compared to unity gradient. And on the right-hand side, this ended up here. You can see that it differs from the unit gradient. It's up to 8% if we go to the highest moment. It's a good question if we should say if the scaling is not present. It's definitely not perfect, but it's still sort of there. I would like to approach this from a quantitative point of view. So instead of making qualitative descriptions, let's just say that we managed to quantify how much it is violated, and everyone can see it here. This is still not the full data. Unfortunately, currently the quota is very limited, so I can't run simulations all day long, but the conclusions won't change. There will be a slight change in the quantitative aspects, but not in the qualitative aspects. So what we have done so far is we quantified this scaling as a preliminary result. And what about collapsing these different multiplicity distributions onto a universal curve? It is, we considered a very fine binning in the jet PT windows. Here I only listed this from 5 to 28. Of course, you can argue that we should just exclude the lowest PT bins, which can be done. What I want to show here is that if we take a more fine binning in the jet PT, then the scaling holds much better, interestingly. And in this case, we can actually collapse them onto each other so well that you can barely see any difference. So this is why I wouldn't say that it's not there. It's just not perfect. But if you compare it to the KNO scaling I showed you earlier, let me go back for a moment. Here, you can see that the violation is much worse. See, these curves are very far away from each other in PP collisions. So compared to that, I wouldn't say that it's not there, it's just not perfect, but the point is that it has been quantified and can be used for model development. So this has been the KNO scaling aspect that I have been working on. I'm still trying out a different unfolding process in which I just unfold these different momenta one by one instead of doing this two-dimensional unfolding, but I don't expect any significant change. And of course, we can investigate larger systems like lead-lead collisions. My analysis code can handle that. It's just that there are limitations in the resources, like running these simulations. But in theory, I can jump into heavy ion collisions immediately, basically. And that's one of my future plans to see what happens there. And let me, is there any questions for this part? Let me ask that.
So I have one, Zoltan. Can I ask? I guess, how can this curve be that it scales on top of each other? It looks like the curves are identical, you said, right? But how does that fit with the slide before saying that if you don't do the multiplicity scaling, the shapes of the distributions are different? Isn't that what I should conclude from the fact that the slopes are not unity? It means as I go to higher multiplicity, the shape is different. How do these two hang together?
Well, it's because this method in which we calculate the different moments, this is much more sensitive in showing us how much the scaling is violated. So even though it seems like it's a very big violation, if you look at how much it differs from unity, but in reality, if you just scale these curves and plot them onto each other, it's not that much of a difference. So this is why I say that I wouldn't dare to say that it's not there. It's not perfect. There is some violation if you go to the higher moments, but
I see. Thanks. Got it.
So maybe a follow-up to that. So I guess like you said, I guess when you were talking about this, you went back to the plot from I think it's not in JETS, but in PP zeta, right? So that was like an extreme violation or whatever. So exactly if you were to like perform that analysis and get this Q as a function, that same kind of plot, what would that level of difference be like from this plot? So like, what's the scale of a big violation? Do you understand?
You mean if I do this exact same plot just for my results?
Yeah, if you were to do the same analysis and get that final plot where you show like an 8% deviation in the data, what would that be for this bottom left?
Well,
approximately, like how big would it be?
But I'm doing basically this kind of scaling with the average multiplicity. So this is what you see here. It's very small.
No, I think she's asking if you take just the overall PP data, not in JETS, the plot that you were just on before, and you get the qth moments from that. Like, how big would the discrepancy in the 9th moment be for the data that we see in the previous plot? Is that what you're asking?
Yeah. I was just trying to understand like how large this deviation would be in that case where it has a big violation. Just an expectation, like 50%.
But how do you connect it to the 8th moment? I'm not sure I understand the question fully.
can I ask also my question, because I think it will help. So if you go back to the one for PP bias, so I mean, if I ask a simple question, okay, what's the sigma of this distribution, right? Which is your
So,
second or third movement, right? It is like significantly different, like, right? I mean, they are off by like 50% basically from first to the last, right? So that influence, that is enormous. Like you will see it in first and second movement, deviation is like 50%.
Yeah, that's what I'm
Right.
Okay.
And in the other one, you have to do like ninth movement. If you do like 50th movement, right, you can get 40%. But in the mean sigma or like third or fourth movement, the deviation is not enormous. So by just looking by eye, they look identically same, right? But if you go for like very high movements, the deviation, right?
Yeah, okay. I've seen a similar badly behaved curves. And in that case, if we do this analysis in terms of these different moments, then the difference would be much larger than 40%. So
even your second movement, I guess, would be like 40% something.
Yes, much more than this. Yeah. Yes, it's not. It's basically within error, within so. In that case, it's much more, at least 40% or so.
So another question I have is like, because I mean, from my previous experience of movements, these high movements especially, the error bars go enormous as you increase the order of your movement. But in your case, it seems like, I mean, because in jets, I would expect less statistics also. So higher error bars are not that big, like. Because I mean, I see like more error on mean as compared to ninth order vertically.
Well, we see larger errors here if you go for a higher PTs. But for these moments, I mean, the fits had very similar errors. No,
I mean, I guess my question is, if you go from Q is equals to 1 to Q is equals to 9, right?
Mm-hmm.
And let's pick your favorite statistic. Let's say the 0.95 data points, right? Vertically. The error bars are almost same or, almost negligible.
Yes, the error is increasing, but not significantly. I'm not sure in my case it should increase significantly. I mean, in a way that you would notice it. I can look into it, but the fits have basically the same error. It's increasing a little bit, but not significantly.
Yeah, because naively you will expect as you increase the order, the error should increase, right? I mean, determining mean is much more accurate than to determine like the ninth order. And then you will naively expect that your error will increase, and that may attribute to your fit and hence the distribution.
Yes, you're absolutely right. And it does increase, just not significantly.
You're hiding quite a bit of it though, because he's dividing 3 by 9 for the ninth order too. So maybe that, I mean, you order of magnitude reducing the error, right?
Might be
actually plotting that.
Might be optical illusion.
You catch what we were saying? I'm sorry, we were like talking over each other. Not like you might have heard it as a jumble.
Okay, to conclude, it does increase, and I think it should increase. It's just, not significant.
Yeah, Yoshi, we have another question from Yoshi.
Yeah. So I guess just a conceptual question. Earlier, you said that the KNO scaling and the PP bar data could indicate some effects of underlying event. So now if you are plotting this as a function of jet PT, I suspect jet PT isn't something really sensitive to underlying events. So I would naively think that you would plot it like as different classes of underlying event multiplicity. So could you explain again why JetPT would be a good scale to separate these classes? I don't know if that makes much sense. Does that make sense?
I'm just trying to remember what I said about this, because I think what I mentioned was the connection to the NPIs and these overlapping color strings.
Yeah, but that wouldn't be something you, like if, that would be something like underlying event multiplicity, right? That wouldn't be necessarily related to JetPT, I would imagine.
Right, what this statement comes from is that we have done simulations checking out the effects of the MPI itself and the overlapping color strings, and they did change the scaling. In some cases, they caused the violation. In other cases, the scaling was very well fulfilled. So at least from the simulations, what we see is that the scaling is sensitive to these effects. But yes, this is something that needs to be understood. This is it's our experience, so to speak, or observation that the scaling is sensitive to these aspects. I'm not sure yet what this means. It's yeah, interesting direction.
Just from my own understanding, you said the scaling in terms of the traditional KNO scaling or the JET study?
The JET study.
Okay.
I'm not aware of the original KNO scaling being studied with MPI effects, but yeah, I don't know. But I was referring to these JET studies that we have been doing. So we managed to quantify the scaling, and again, I'm refraining from making these qualitative statements of whether it's there or not, because it's sort of complicated in this sense. We have quantitative data. That's the best anyway. So if there are no more questions, then in the remainder of this presentation, I would jump to the heavy flavor studies, and we'll try to motivate some other measurements which should be done in ALICE. So here's some backgrounds. When these heavy flavor hadrons are created through the fragmentation of the heavy quarks, then we can describe their production in these high energy collisions usually with this factorization approach, in which we convolute three independent terms. One of them is the incoming parton density functions, the parton-parton scattering cross-section, and the fragmentation functions. So we try to calculate these production cross-sections. And the traditional assumption is that the fragmentation functions are universal. In other words, they are independent from the collision systems, whether you consider electron-positron or proton-proton collisions. However, recent experimental results coming from ALICE, CMS, and LHCb shows that the charm baryon production does not support this assumption. And let me show you why. Here is an experimental result from ALICE. On the horizontal axis, you see the PT of these particles. We consider the lambda c over the meson ratio. So basically, we take the production of the lambda c baryon and divide it with the d meson. and the cross section is shown on the vertical axis. And the dots are the experimental data. The white dot is at 5 TeV, and the blue dots are at 13 TeV PP collisions. And you can see that there is an enhancement if you go for lower PT values. However, if you take the simulations that you get from running Pythia, using this assumption that the fragmentation functions are universal, in which case you take the parton density functions, fragmentation functions, this third term from electron-positron collisions. This is how it works in Pythia. Then you see this dot. And so it's very far from the experimental result, as you can see. So the simulations can't predict properly this enhancement, and this is something that needs to be understood. Several scenarios have been proposed to explain this observation. For example, we can assume an augmented set of charm baryon states. In other words, we might have particles which are not part of the data book, and we just haven't detected them yet. Or we can use certain coalescence models like the Catania or quark combination mechanisms. However, the model that we investigated is the so-called string formation beyond leading color. These have different variations, which are called mode 0, 2, and 3. These are shown here with purple dotted lines. And you can see that this gives back this enhancement that you can see in the experimental results. Not all three variations describe this enhancement quantitatively, but the mode 2 is pretty good, this one. So we consider this mode 2, and it's basic practice lately to only consider this color reconnection mode 2. So again, there are many models which can describe, at least qualitatively, this enhancement, but we don't know which model is the right one. So what we try to do here is to try to at least rule out one of them. And for that, we propose some measurements which could be done in Alice, which might help differentiate between these models.
Zoltan, can I ask a question?
Yes, sure.
So for the string formation beyond leading color, if you're saying that this is this enhancement could potentially be due to some dependence on the PDF or the collision system, what is it about the string formation beyond leading color that, how does it get information about the collision system to, I guess, the fragmentation? Like what is being modeled there?
It's this model is basically added to Pythia, in which you just you have more final states than usual. So here in this little picture, you can see that you can connect different partons, so to speak, and this will cause this enhancement. And one of its advantages actually is that you can simulate this in Pythia. The other ones, not so much. So this can actually be studied, and this is why we took this model, because it can be investigated with these Monte Carlo simulations.
So the model is a difference in the fragmentation, but so you're just assuming that this type of fragmentation would be present in PP collisions, but not in E plus E minus, and there's not really a reason why.
Yes, essentially it's just a different fragmentation model which you use in the Monte Carlo simulation, and you will have more final states with these particular properties. That's in your judge, yeah.
So I think does it also have to do with higher multiplicity in PP collisions? So you are more likely to have these QQG to be in a closely, like they were more likely to be close in terms of phase space so that they could form these extra connections. Like,
yeah, if I understand correctly, then yes, what you're saying. But yeah, the multiplicity dependence is it's not fully understood yet. So this is actually one of the things that we investigated, how this depends on the multiplicity. So yeah, I'm not sure about the exact multiplicity dependence. I mean, from this mathematical point of view.
I was just trying to, I guess, maybe trying to build off of Andrew's comment that it probably isn't the case that you just manually add in some process that doesn't exist in E plus E minus, but rather it's something that would happen in both cases, but only happen more significantly and have a obvious effect when you have higher multiplicities.
Well, in reality, these Monte Carlo simulations are just an approximation. So according to this model, you're not adding something artificial. You actually add something which was neglected.
Yeah, but what I think Yoshi was asking is that if you, for example, you were able to prove without a doubt that the string formation beyond leading color is what's happening in the PP collisions, that there has to be a reason it's not having an effect in the E plus E minus collisions if it describes those well without it.
Yes, and proving it that it's the case is, I'm not sure it can be done. Instead, what we try to do is to give a method which can at least rule it out. So not the same, but yeah, because the other models can also explain this jump baryon enhancement. In some cases, even better in certain particles, in case of certain particles, because this can be measured for higher mass baryons as well. And then these different models perform differently. So I'm not sure it can be proved that this is the case, but at least I think we have a method which could rule it out. So, but let me go into details if there are no more questions to this part, and then maybe I can shed more light on this.
I just have a quick question. I mean, very quick. It's actually on the rightmost panel, Zoltan. I'm just curious as to why you think it is that none of these CRPLC modes can actually describe this feed down from the sigma sub c's into the lambda sub c's at all, whereas the actual other two panels seem to be kind of described by at least one of them, yeah? So like, why is it that this feed down, I guess this, I mean, it's a fraction, right? A fraction of the lambda c yield that comes from the sigmas. Why is it that it seems to be overshot by all three modes? At least, you know, in the low PTM.
For the lambda c baryon, all these models perform pretty well. But if you go for higher mass baryons like the sigma, or consider baryon per baryon ratios, then the other models in some cases perform much better. So, but none of them are perfect. So it's not enough to differentiate between them. And I didn't say that these different models can't describe these ratios, or that we can immediately rule this model out. I'm only saying that for the lambda c ratio, lambda c over d meson ratio, they all work pretty well. And within the enhanced caloric connection model, the mode 2 is the best performing one. And for higher mass baryons, they perform differently. to actually rule this model out, you need to do the measurement in Alice. And this is why I am trying to motivate that measurement. I will show you exactly what we want to measure and see. So again, confirming this model is not easy, but maybe it can be ruled out. It's used pretty, this is a very prevalent model. It's used all around the place. So it would be interesting to give a measurement which can tell us something about its correctness or not. Please tell me if I didn't answer your question.
Yeah.
So then let me go on to the question of multiplicity dependence. It turns out this is a very recent result from Alice, that this ratio depends on the multiplicity. We actually made these predictions before this experimental result came out. It just took some while to publish the results. So anyway, we expected this multiplicity dependence to be there, and the experimental results confirmed that. Excuse me. Here they took the usual multiplicity definition, and also we can take the forward multiplicity description. So the goal would be to understand the origin of this enhancement. And the exact question that we asked was to study whether this enhancement comes from the jet region or the underlying event. And for this, we can use certain event classifiers. Let me show you these observables that we can measure. One of them, the first one, is the well-known event multiplicity. You just take the charged final state particles within this pseudo-rapidity region, and you can take the forward multiplicity much closer to the beam axis, and you can introduce these event activity classifiers. One of them is this RT, which excludes the jets from the leading process. So this will be our underlying event activity measure. And similarly, we can introduce a jet region activity measure, which will contain the leading processes. You can see the definition. We just, in the underlying event activity case, we take the multiplicity in this azimuthal region. It's close to in this transverse region, and normalize with the average. And basically this will be our modified multiplicity measure. And it will, the higher this value is, the more active the underlying event is. That's the idea. And this is the jet region activity, similarly for the jet region. And both of these event activity classifiers can be used when we have a triggered particle. But if we don't have one, or we don't want to use triggered events, then we can use the sphericity according to this equation, which will tell us how spherical or jet-like the collision event is. It is a little picture that shows you that this is a value between 0 and 1, and the closer it is to 0, the more jetty the event is, and the closer it is to 1, the more spherical or isotropic our event is. So first of all, we can just do the very simple measurement of these ratios as a function of the particle momenta for different multiplicity classes. On the left-hand side, you can see the multiplicity classes. On the right-hand side, the forward multiplicity classes. Here I just want to show you that we are in agreement with the Alice results. And in fact, this came out even earlier than the Alice results. And they are very similar to each other, which shows us that these two regions are just minimally correlated, so to speak. So we can take samples from these different regions, and we don't expect them to correlate in a very strong way. And if we go to these yes, just want to mention here that we can also differentiate between what is the origin of these particles, like coming from a direct decay or whatever. It's not so important. Let me go to the event activity classifiers. On the left-hand side, we have the underlying event activity classifier on the left-hand side, and on the right-hand side, we have the jet activity classifier. And what you see here is that if we calculate these ratios with different underlying event activities, then this enhancement will differ. This basically tells us that the enhancement depends on the underlying event. However, if we consider different jet activity levels, then you can see that for low momenta, the enhancement is practically the same. In other words, this tells us that it doesn't depend significantly on the jet activity region, on the jet region. And there are some dependence if you go for higher PTs, but that's a different region. We usually consider these low PT regions where the real enhancement occurs. So this is the region of interest. So let me say again the physics message. The enhancement depends on the underlying event, and it doesn't depend significantly on the jet activity. This is the main message here, at least in this particular model. And what if we don't have a triggered particle? Then we can take this sphericity, as I mentioned earlier. Here we choose a particular multiplicity class and then divide these events according to these sphericity values. You can see that the enhancement depends on this sphericity. Here I included in the table the exact binnings that we have used. And to give a better view, what we do is to integrate these curves. So we are going to get a value for every single curve. And then we can plot this for the different PT values. This is what you see here. On the horizontal axis, you have either the underlying event or the jet activity classifier, depending on the color. And on the vertical axis, you have these integrated curves. And the conclusion is that if you consider the jet region activity, here this purple color, then you can see that it's very close to the mean bias. So it doesn't significantly depend on the jet region activity. And if you consider the underlying event activity, then there is a significant difference. And if you go for non-triggered events and do the same measurement for this sphericity, then in this case, in every multiplicity classes, there will be a difference according to how isotropic the event is. However, let me bring your attention to these extreme values, the very low multiplicity and the very high multiplicity events. If we have very low multiplicity events, then dividing the events according to the isotropy doesn't make a big difference. However, if we have high multiplicity events, lots of particles, and we divide these events according to the isotropy, then there is a big difference. The enhancement is much bigger if we go for more spherical or more isotropic events. And this serves as a cross-check. If you think about it, this just confirms the other results, because if you have a low multiplicity event, then the jet will dominate. And in other words, the jet region will be very active. So it doesn't matter how we divide according to this sphericity, the enhancement won't depend on that, because it depends mainly on the underlying event, not the jet region. And if we take high multiplicity events, then this classification according to the isotropy will become much more pronounced. Again, this serves as a cross-check and brings us the exact same physics message, just from a different point of view. So again, just let me say the physics message again. In this particular model, using these event classifiers, we showed that this enhancement is connected to the underlying event and not the jet region. And what we want to motivate here is to do the exact same measurement in Alice and see what we have there. In other words, if this enhancement in Alice depends on the jet region or the underlying event, how these different contributions come into play, and this hopefully can be used to maybe even rule out this particular model or show that it behaves the same way as expected. And as I'm running out of time, just briefly mention that there is this new observable flattenicity. It's quite recent in Alice, proposed by Antonio Ortiz and Guy Pike. And this connects to earlier measurements. Here, it's just another way to classify these events. And we can do the exact same measurement and arrive to very similar conclusions. Let me just go through this quickly. And finally, before the summary, I want to mention that we can also consider the beauty production. This is also a fascinating area and will be very significant as we go into Alice 3 and into the future and have more precise measurements. Here again, we can do similar measurements with these event classifiers. So let me quickly summarize. I showed you that jets can be utilized for a whole lot of things, including searching for certain scaling effects. Here I did the KNO scaling measurement in the Alice data and motivated other scaling measurements which can be and should be done, in my opinion, including the search for this R-fix scaling, which might be there, might be not. Also showed you how heavy flavor can be utilized to look for these different effects connected to the underlying event or the jet region, and maybe even used to differentiate between well-performing models, like the enhanced color reconnection model. And I'm looking forward to analyzing the run-free data and expanding these measurements, and also, of course, the Alice 3 in the future. And with that, let me thank you for your attention and wish you a happy new year. Thank you.
Thank you very much, Zoltan. Do we have any questions? Go ahead, Sierra.
Yeah, I had one, Zoltan. Thank you for the nice talk. Could you go back to 21 or 22, somewhere in there?
21.
So, correct me if I'm wrong. So you said that the dominant contribution to the charm baryon to meson ratio is the underlying event, is what you're seeing in these simulations, and that would be evidence for ruling out the color reconnection theory if you saw that in Alice data. Is that what you said?
No, not exactly. What you need to do is to measure this in Alice, see what you see there, and then compare it to what happens in the model. And if you see a different dependence in the experimental data compared to what you see in this particular model, then the model can't capture this dependence, so it's not correct. We don't know yet. This is why I try to motivate this measurement.
I see. Is it possible that you could have multiple effects like color reconnection and coalescence? And so maybe if you put more effects and make a more sophisticated model, you could get the whole picture eventually? Or is it somehow that they don't play nicely and you can't have them together, if that makes sense?
Yeah, I think so. To me, all these models seems like they capture something, but none of them are perfect. Again, you can see this if you do these measurements for higher mass baryons and taking baryon to baryon ratios, they perform differently. So it's as if they all capture something, but none of them are there yet. Of course, the augmented set of baryon states, that's a good question. That might be just not there, or it might be the explanation and all these other models are not needed. I'm not sure how these overlap or how these can be reconciled with each other exactly, but the picture I see is that many of them manage to capture something important. So it would be really crucial to see if at least one of these common models perform well or not in the experimental data.
So I guess, put simply, if you did measure this and it didn't match this particular prediction, would you say that the color reconnection isn't there, or just that it's not the whole story?
Well, the theoreticians will probably try to adjust it.
Sure.
So, but if we see a big like if you see in the experimental results that it's connected to the jet region, then that's such a big difference that I just can't see this model work. So I see a real possibility of actually ruling it out completely without these, you know.
Yeah.
So I guess going 2 slides ahead, because I haven't really seen this before at the 23. The hedgehoggy events.
One more
Oh,
slide.
sorry. Yeah. So
You can.
yeah. So the flat versus hedgehog events. Just because I haven't seen this before, would you mind explaining quickly, I guess, what physics is meant to be highlighted by a very hedgehoggy event? And is it similar? Is there like a correlation between hedgehogginess and jettiness? And so is this a true like extra axis? Like do you, since you see the same thing across flat or hedgehoggy events as you see like non-jet circular versus jetty events, does that say something new, or are they somewhat similar?
I can tell you right away that they carry the same message. So they also carry information about the jettiness of these events and indirectly about the underlying event activity, and classifying the events according to this flattenicity measure also shows us that the enhancement depends on these classifications, and the message is the same. Let me go here. Here you can see that this ratio does depend on this classification, and the message is essentially the same. It's just there are technical differences how you measure this flattenicity. In some cases, it can be a better measure. Still under investigation if it's a preferable choice over sphericity or not.
Is it, sorry if this is off base, but if you go back one slide, is it that the flattenicity tells you more about whether events have a multi-jet topology? Like if it's very hedgehoggy, it's a multi-jet event, which maybe, I don't know if this ferocity gets at that.
I'm not sure it carries more information. It's more like the same information with a different point of view, in a sense. Like you can see 2 extreme cases. Like here, if you have a very like a uniform distribution of all these particle PTs, then it's more of an isotropic event in this sense. And this particular event has 0.58 flattenicity value, and the other one is much higher when we have a more jetty events. It's more hedgehog-like, so you have more of these dominating jets inside the event. So in a way, gives you the same information but calculated differently. So it's a good cross-check. You divide your event into these different cells and then normalize them with the averages. Even by event, you do this measurement and then you get the flattenicity.
So Zoltan, let me make sure I understand those two plots. I mean, the difference really is the number of multi-proton interactions that the models put in, right?
Right.
So how do you actually, you will just take the flattenicity and kind of scan through the different events in terms of what the flattenicity is?
Right, exactly.
And then if you look at the events, basically the distribution, as you have eta phi, of course, the jettiness, if it's more jetty, it's going to be like the one on the right as compared to the left. And you're going to take the lambda over d values more or less as a function of flattenicity to see if
It's a function of the PT and for different flattenicity classes. Yes.
Okay. I mean, so in PP, maybe this is getting back to the first part of your talk. You know, you have lambda over d enhancement basically due to jets as compared to anything else, right? And then I guess, I mean, you say it depends on the jets, the enhancement in PP.
It depends on the underlying event activity much more. And it doesn't depend significantly on the jet processes, the processes inside the jets.
Can you show me that plot again? Maybe.
Yes, sure. Here.
Right.
Here, these different classes basically measure how active your underlying event is. You can see that as it becomes more active, you go for higher values. As you go from 1 to 5, the enhancement becomes bigger. So the enhancement is maximal when you have those events which have the most active underlying event in a sense. On the other hand, if you classify the events according to the jet region activity, then the difference is not there. It's essentially the same enhancement. So it doesn't depend on how active your jets are in a sense.
Okay, and then if you were to go to lead, what do you haven't done that, but what to do? I mean, what do you expect qualitatively as compared to PP that would affect the lambda over d ratio? You know, when you compare jets to the event, underlying event. I mean, because you have parton energy loss, you have suppression. What does that do to lambda? I mean, qualitatively, what do you expect that to do to your lambda over d ratio in terms of jets and event backdrop?
I'm not sure about that, to be honest.
Yeah, I'm just wondering if you look at jets in general, looking at lambda over d, and you increase the multiplicity, I guess it hasn't been done. But what about the lambda over d ratio versus anything in jets? I don't know, maybe Laura knows. Has that been done?
Yes. I think it's been done in PP, not from the functional multiple. I think the fragmentation, the lambda over d fragmentation has been measured in PP. recently. I don't know if it's published. I think it might be a preliminary result. It is, I think it is a preliminary result.
Okay, I guess that partially answers my question to Zoltan, and that is if you expect the if you measure the fragmentation, you expect it to deviate from PP if you measure the fragmentation function because of the parton energy loss, right? Yeah, so it's a multivariable question and measurement, I guess. Yeah, so I guess it's interesting to do. I mean, you would expect more underlying event as you have more quenching, no?
Yeah, definitely.
Okay, so then it's looking at the fragmentation function difference in lead versus PP in lambdas and Ds in a jet compared to the underlying event to understand actually what happens. Okay, sorry, I'm thinking in my head on the spot. So let me ask another question. On slide 8, I didn't quite see the left figure. I think it's the left-hand figure where you have, is that not where you say, okay, you definitely have scaling violation, but what are the energies there? So you have scaling violations above 200, Jeff. Is that true? Is that what that's meant to show? And
yes, it starts already at 200 GeV, and yes.
So if you have scaling violations already, what does that I mean, what are you plotting? That's N over N. What's the denominator there?
This is the average, the average.
The average N, right. Okay, so that's KNO.
Yes.
So how do you expect these scaling violations at the higher energy to affect what you've measured?
You mean in the inside jets?
Yeah, I mean, so you say you have scaling violations at high energies, and then you go to high energy PP and you measure, and you're looking for scaling, and you see approximate scaling, I assume is what you might call it.
But in my case, these are the jet PT, not the collision energies. And indeed, as we go for a higher jet PT values, then we observe a bigger difference.
So in this figure, the scaled multiplicity is N over N average, or what?
Yes, we scale them together with that procedure, yes.
So the scaling violations you expect to be really kind of on the right tail of that, a couple orders of magnitude down, right?
Yes, somewhere here should show up, but these are these.
Right, I was looking at the figure right before this.
Sorry.
Yeah, if you look at the left figure, you have scaled multiplicity, and basically above 2 or so is where KNL scaling breaks. No, that would be figure 8 that shows that.
Well, it's just, I'm not sure we can conclude that from in observing on the horizontal axis where it differs. It's just like the tails of these multiplicity distributions don't overlap properly. But here the more important data is the jet PT values themselves. I guess we can quantify it by taking some kind of ratio between these multiplicity curves, and then we get an exact number which will quantify for you how much they overlap or not.
Okay, sorry to prolong this, but if you go back to slide 8, this lower left plot shows that the scaling violations occur probably actually above 1.8 or something, right? And are you not looking already below? I'm just trying to answer my own question, sorry. So the scaling violations wouldn't hurt you unless you were above 1.8 or so, but you're saying that the N average changes, and so it's not directly applicable until you look at those figures that you showed me, which go from left to right and don't have a unit slope, right? The N average changes there.
The average is
like there, you have log 10 of N, and then you said no, but you can see the violation or differences more, and you showed me a later plot. Sorry, I don't have all the numbers. Yeah, I think it was the previous one.
So these are different dimensions. What I mentioned was that as you go for higher PT jets,
yeah,
then you see these differing much more. So on the one hand, you can quantify this by what is the jet PT value above which you observe this violation, or what is that scaled multiplicity value at which these distributions start to differ. And yeah, I guess we could attach a value depending on where they start to break down in terms of the scaled multiplicity. The average multiplicity scales. I mean, it's shifted for higher values as you consider different jet PTs.
So Zoltan, maybe part of John's question is, where you, with the previous experiments, measurements, the scaling doesn't break down until about, well, I guess it's already there at 200 GeV. We haven't got a lower square root S. But then you say you replaced jet PT with square root S by saying these are the Q of the collision sort of mapping. That's why jet PT is a relevant variable in your study, because you say that's the Q of the collision and closer to what's being measured in E plus, E minus. But then wouldn't you have to get up to 200 GeV jets to see the violation coming in?
That's a good question.
Because I thought that was why you switch in the jet PTs. You say this is a way of just getting what the single Q of the parton interaction is, which is closer correlated to what you measure in square root S in E plus, E minus. Because the square root S in PP, as you said, had all the NPIs and other things in it. So it's not really a true mapping of the Q, right? That was your argumentation, I think. Yes.
Yes.
Why you switched to jet. But now you're at very low, well, I mean, compared to 200 GeV, low jet PTs, right? Because in your one where you have lots of them, what is the highest jet PT? I wasn't looking at that in your measurement.
About 115.
No, this is NPA simulation. The next slide.
Yeah, but I'm talking about data now. In the
Okay, can you go to next slide?
Oh,
The one after, yeah, this one only goes to 20.
But if you go to your PIPIA, which is purely PIPIA, it's not violated even at the high Qs, right? That was what the previous bit of your analysis.
One data point that's kind of off. I don't know.
Yeah. Well, but he goes, up to 400, right? So
Okay, but that data point, maybe I shouldn't just pick up on one data point. But
they start to differ, but not much. Like they don't lie on top of each other perfectly. You can see that there are some there is some violation, but yeah. Sorry. But yeah, in case of PTA, we can go up to 400 GV. In data, only up until 115, because the unfolding process is not very good above that. So
do you have our data? Did we have that, Billy? Is that a plot you showed us? Yeah.
which data are you referring to?
I think she's
The
wondering if
average
you had
100.
the higher PT. If you have, so, because you showed it up to 28, but she's wondering if
here,
you have like, if you have these, or if you have something but for above 28, but.
Just let me clarify. This is data. Here I just plotted the lower values to show you that for lower PT values, they really lie on top of each other pretty well. I, of course, have the other ones, but the picture would just get too involved. But you see the difference as you consider higher PT jets. So interestingly, in data, already at around 80 GV or so, you see this violation. But you can see it here, basically. See this higher PT values. So
maybe that's something that people are, so what are the different points on the left plot?
the different points are the different jet PT windows. And the different curves are the different moments.
And then you can see the, yeah.
So I guess what you're saying is that the 8% deviation in the ninth moment that you do see, if you just calculated off the ones that you show in the previous slide, you wouldn't get that big a deviation? Like, is that deviation coming from the higher PT bins?
Did you hear
that? Could you repeat your question, please?
So I guess in the curve where you have them all on top of each other, and I think this kind of goes to our point of confusion a little bit earlier, is that when they're all on top of each other, that's only the lower PT bins. But then this 8% deviation at the ninth order taking into account the higher PT bins as well, correct?
Yes. Sorry for the confusion. Yes, exactly. Yes, this takes into account the whole jet PT range.
So, like, do you think maybe this follows on the question? Do you think that if you were to say restrict to higher PT, you would get so if you cut off the bottom 4 points on the left or something like that? I can't remember what PTs there are, so just assume. Do you think you would then get more violation? Is that what you're saying?
Well, it depends, because these differ from unities. So if you take a smaller region, then you can more or less fit a linear curve on them. And I guess what's problematic here is that you don't have enough data points if you cut out too much, and then you can just fit the linear curve on them. You really need to consider the whole range.
But if you fit the first 3 points on the left plot, like 0.9, 0.97, and 1-ish, and then maybe if you just fit those 3 points, and then the rest of the high PT points would not lie on top of that line, right? And that would be somewhat indicative of a violation.
I see what you're saying. Yeah.
Actually, that would show that there is no violation, because if you just fit on fewer points, then you won't see that difference compared to a linear curve. So you have to be very careful to use enough data points. So if you don't use enough data points, then whether you fit for the lower PT values or the higher PT values, you will get scaling.
So if you only fit the lower PT values, the higher PT points wouldn't fall onto the curve you fit for the low PT curve.
Yes, they start differing as you add these extra data points.
But would that be like an indication of scaling violation?
Yeah, yes, as it was mentioned, as you go for higher energy jets, they start to differ. We just can't go to above 115 or so, unfortunately, to get a clearer picture.
Any other questions?
Not really a question. Zoltan, do you think you can show me just real quick? Because I kind of forgot where it all was. The slide right before your summary, I just need to look at it real quick. Where you show the lambda B to B ratio. I could always look at the recording, but I just forgot what it would look like. Just way at the end.
Yes, I know. Here.
Yeah. Okay, cool. Thanks. Oh, that's all I needed to say. Thanks.
Fernando has predictions. This is why he wants.
No, like integrating my head. So
Okay, so anyone else have any questions? Okay, well then, if not, let's thank Zoltan again.